a few more counting problems, and we'll do a review for test 3. We do have some review sessions tonight by your TAs. Tonight and tomorrow. So it's in EB2 3211. That's also posted on your Piazza page. I also have your tests 1 and 2 up here at the front. So if you haven't picked those up, please do that today. I've been getting a lot of questions about the Guaranteed C policy. It is on your syllabus extremely clearly. I've reposted it on Piazza. The only thing that isn't listed on that is listed here is that you need to turn everything in for a Guaranteed C by December 5th. So, well, not turn it in, have it all checked. So you need to work all the special tests, have them checked by a TA or myself. You need to work any problems that you missed on any tests, have them checked. Rework your homeworks until you have at least 70% on them. Just ask for extensions. Make sure you do all the labs. Show up to the test. Then at the end, you bring your rework tests and special tests to the final exam, and you tell me that you're giving it to me for the Guaranteed C. So that's all you do. If you've done all that, then you will get a Guaranteed C. Now, if you don't need a Guaranteed C, but you kind of want to guarantee a little bit, you can actually bring all of this to your exam, and if you are close to a grade cutoff, we will round you up. So if you feel that, you might have an A minus that you might turn into a B plus, you might want to do these things also. But we'll only round 0.6 points at the most for that. So it's up to you to decide if you want to do it. As a matter of fact, if you do it, you'll probably get those points that you need anyway without me having to do anything. Okay, another logistical item is thank you all for making Piazza posts. Some of you have started making a little wiki for the different questions related to each homework. And like I said, I can't make those because you guys can't edit them after I make them. So I appreciate it when you guys make them. If someone can do it for the other homework, so we have them for 7, 8, and 9 homeworks. We might have one for practice test 2. So if any of the peer tutors wants to go back and do that during your hours, would love that. And also one for each of the practice tests and one master one that links to all of them. That would be so awesome. So because when everybody's studying, it will be really helpful if they could just click through the Piazza and see all the discussions about the related homeworks and practice tests. Any logistical comments? Okay. All right, so we're going to do some more counting problems, mostly because we need lots of practice, and you really, really, really should look in your book for more practice problems. There's a lot of examples, and the more examples you read, the better you'll be able to understand how to set up counting problems. Here's one. It's basically like a series of the problems in your book are about this lottery where there's 100 tickets and 3 winners and 1 grand prize winner, meaning there's a total of 4 winners. We have 100 raffle tickets, so we want to figure out how many ways to award the prizes. The first thing we need to do is decide if order matters. Does order matter? Okay. I have yes, no, and sort of. What does it depend on? So if all the prizes, like if the 3 winners and the grand prize winner, if the grand prize winner gets the trip to Tahiti and the other prizes are free Cokes, we care which one we get, right? We care if we get the grand prize or one of the other ones, but we don't care which of the other ones. So that's actually where order sort of matters, but not for all of them. So if they're all different prizes, it's going to be different. So let's just say we have Tahiti and Cokes. So the first one's going to be that, and then 2 through 4 will be Cokes. Let's solve it for that. Okay, so what I've recommended in the past, and I still recommend, is that you choose your winners first, and then you figure out any ordering. So out of 100 people, I'm going to choose 4 of them to be winners. Then out of those 4, I'm going to choose 1 of them to be the grand prize winner, and the other 3 automatically get their Cokes. So that's all we need to do. There's many, many ways to do these problems. Another one I could have done is said, out of the 100, choose a grand prize winner, and out of the remaining 99, choose the 3 Coke winners. The nice thing with the second one is that those top, well, it's that the bottom numbers add up to 4, which makes me happy, but the top numbers don't add up to 100. That doesn't make me happy, but there's nothing we can do about it because that's how this problem is. So let's verify that these are the same. So C104 is 100 factorial over 96 factorial 4 factorial, and then C41 is just 4, right? There's 4 different ways to choose 1 out of 4 things. And the second one is 100 factorial. Actually, it's just 100 because C101 is 100. And we multiply that by 99 factorial over 96 factorial, 3 factorial. Okay, so this is 100 times 99 times 98 times 97 all over 6. And that's the same on the top. And it's all over 4 times 6, and I multiply by 4. So, lo and behold, those 2 things actually are the same. Once I cross out the 4s. So, it actually is a great idea to think of 2 or 3 different ways to solve a problem, and then solve them those different ways and see if you get the same number. If you do, then you're pretty sure that you've got the right calculation going on. Yes? I want both of those. So the problems will specify, give the formula in terms of CNK, PNK, or factorials and exponents, and also expand for factorials and exponents. Yes? The question is are there any situations where one way would work and another way would not? Yes, but usually it's because we make a mistake. So if I use 2 different methods to calculate the same thing, what I'm trying to do is actually think about my reasoning and make sure that my reasoning actually ends up with the same number in both cases. Because what I want my reasoning to do is to separate all the different things I need to count into the right sets and choose the right things out of them. And so if I try 2 different ways and my answers don't match, then I'm going to look back at them and see why one of them might be wrong. Okay, let's do the same problem, except instead of Tahiti and Cokes, let's say there's like 4 prizes that are all good, like Tahiti and then, $2,000 and then a new luggage set and then a Coke. Yes. So the question about C41, shouldn't that be 4 factorial over 3 factorial times 1 factorial? The answer is yes. Those 2 numbers are equivalent. 4 factorial divided by 3 factorial, 1 factorial is 4. There are, like I said, many, many equivalent ways to write numbers. It's okay with me if you write 4 when it's actually C41. That's okay. You don't have to put the factorials for that. Okay, so we were going to do it if there were 4 different prizes. So 4 distinct prizes. So we have 100 tickets. We have 4 prizes. And so that's easy. It's going to be P104 because all the prizes are different, and that's going to take care of that. Now we have to write the formula for that, which is 100 factorial over what? Is it 4 factorial? Is it 96 factorial? 96 factorial. And why is it 100 factorial over 96 factorial? So one answer is because I subtract 4. That is true. What else? Order does matter in this case. That's right. Why I wrote a P, because it's permutation. So they're all different prizes. So it actually matters which one you get. Would you like to go to Tahiti, get $2,000, get a luggage set, or get a Coke? Does it matter to you which one you get? Yes, it matters. And if it matters, then we want to count with order. Yes. So there's like a ghost factorial going on here. So my first choice, I have 100 choices for the grand prize winner, then 99 choices for this runner-up winner, 98 choices for the third prize, and 97 choices for the fourth prize. That's why we have this formula. So don't just memorize the formula. What you need to remember is how to understand it, how to draw the picture that we made to get the formula, and then you won't mess up, because whenever you write down that formula, you can double check it and make sure that you're using this picture. So the reason why we use that is because always this set of blanks here is always going to have a number of terms, however many choices I'm making. And it's a pain to have to write that many things. And this formula allows you to write 2 things, which is why we use it. Questions on this one? Yes. That's right. If the prizes are the same, we use combinations because it doesn't matter which order you get it. You know you're getting a Coke. Yes. I love that question because I actually really like to do it that way always. So the question is this the same as choosing the 4 winners and then ordering the 4 winners? Absolutely. Yes, it is. So that would be choose my one out of my 100, choose 4 people, and then you multiply by the ways of ordering 4 people, which is P44, which is what? 4 factorial. So this would be 100 factorial over 96 factorial, 4 factorial times 4 factorial. If you want to write 4 minus 4 factorial, you can. That is 0 factorial, which is defined to be 1. And then that's why this comes out the way it does, is because these 4s cancel out, and that's actually just 1. Thank you for asking the question, because I actually always do them this way. Because if you have any mixing of ordering and not ordering, it's really a pain and very confusing. So I like to do everything without order and then fix the ordering at the end. So when counting problems, what we're usually trying to do is reduce the problem that we're given into a set of small problems that are not so hard to figure out. Yes, Philip. Well, let's just do this one. It's very similar to what you're asking. So let's say we have the same situation, 100 tickets, 4 prizes. They're all different. We know that 1 out of these 3 people wins, and 2 out of those 3 people do not win. Okay, so going back to our strategy of choosing our winners first, then what we can do is say we can choose out of these 3, we're going to choose 1 that wins. Now, the second one, there's a slight problem with this one. What is the problem? One of the possible losers is the same as one of the possible winners. When you have totally disjoint sets, this is a really easy problem. So let's just do this problem as if there was instead these 3 numbers. So let's solve this one first, and then we're going to come back to this one. Okay, now out of this set, How do I choose? What do I do? Well, I don't actually have to choose the people who don't win, right? I don't need to choose them because they're not winning. So I'm choosing winners right now. So how many people are left? So remember, we're ignoring this, okay? We're just looking at this, and we've already chosen 2 of these to be winners. We know that, one of these to be winners. We need to choose, so at least 2 of those don't win. So basically what I can do is subtract 2 from my number of people left. So the number of people left after I did this is how many? So how many people left can win? Well, so we chose 1 winner out of here. So are there 99 other people that could win? Without looking at this, so just without looking at this, out of this, how many is it? 99? It depends on how you read this, right? It doesn't have the word exactly in front of the word 1, right? Let's solve it for exactly. If it's exactly 1, then we have 97 people left who can win, right? At this point. But then when we start, so there's 97 left at this point. But now, after we've done this, and now that we consider this, we have 2 of those people don't win. So out of however many, 97, I have to subtract 2 of them, right? So out of 95 remaining people, I'm going to choose the other 3 winners. And then after that, I order my prizes. So I've already chosen my people, and now I'm going to order them. There are 4 of them, and I'm going to order all of them. So we modified that problem significantly, right, so we could solve it. So if we don't use the word exactly, let's fix it now. So now we're going to fix it. So this was exactly 1. And so there's the criteria there for this answer. Now, if I do at least 1 from the first group, and the same here, no more than 1 of the second group, then actually the number of people I have left that could win is 99 after doing my first choice, because the other 2 could win something. So after I choose a winner from this group, the other 2 could be thrown back in the hat. That's replacing them into the choice pile. Yes? No. Our first problem, what we solved is, if there was exactly only 1 of these can be a winner and none of the other 2, then the number of people left who could win is everybody but those. So after I choose a winner out of here, the 97 people left are who I choose from. And then out of those 97, I know that out of these 3, at least 2 of them don't win. So I knock 2 of them out. So that gives me my 95 here. And then I choose 3 winners out of that. But I didn't actually say that I might have to knock 3 out. So one of these could possibly be a winner. So I didn't do exactly on the second one. Now we're trying to do the problem where we get rid of the exactly on the first one. So there's 2 different answers to the question of how many ways are there to choose winners after I choose who wins out of this set. I did do exactly. I didn't do exactly with the losers. I did do exactly with the winners. because the remaining counting, so the question is, why did you only remove 2 instead of also removing 3? Because I'm excluding 2 of them, but all the choices that are left, some of them will choose one of these remaining people as a winner, and some of them won't, so I'm actually counting both. So let's say that 63 and 27 don't win. If I take them out of the pile, all the counting that's left takes into account whether 3 actually gets to win or not. That was a good question. And the reason why we're treating these differently is because one of the piles is about winners and one of the piles is about losers. And so when we're talking about what we need to count from, we just need to count people that could possibly win when we're starting to choose who we could choose. So that's why we're treating the sets differently. So now we're trying to say at least one of 62, 99, and 100, and no more than one from 63, 3, 27. So the only difference is that after I make this first choice, there's 99 people left that could win. So then after I'm going to subtract 2 because of the 63, 3, 27, at least 2 of them have to lose. So I have to take out 2 people out of my 99. So I'm going to do C97, 3, and again at the end I'm going to multiply by P44. So the only difference between these two is this number of people that I got to choose from that could possibly win after I choose how many people get to win, at least one person winning from this set. So the reason for doing this problem is it illustrates how it really matters how you read the problem. And so if you're going to read the problem and you're like, this could go either way, you need to write which way you assume on your test paper. Yes? Yes, you may assume either way as long as you write what you do. If I have not been completely unambiguous on the test, you can write whatever assumptions you have and then solve that problem. And then what I recommend you do is work the rest of your test. And if you're just sitting there with some extra time, go work the other possibilities. And then you can get some extra credit. Yes? That's right. We haven't done the 62 yet. We've only been doing the 63, 327 problem. Because when I wrote the problem, I meant it to be confusing, but I also think we need to solve the less confusing problem first. No. So remember that last time we talked about tree diagrams? So we need to break up our world into whether 62 gets chosen or not for solving the first problem that I gave you. So let's specify that problem. So we know that one of, and basically if I read the word one, you should usually assume at least, because think about this prediction as someone with a crystal ball is making this prediction. And they say 1 of 62, 99, and 100 is wins, and 2 of 62, 3, and 27 lose. They're going to count themselves right if at least one person from there wins, right? And if one person from the second one wins, that's fine too. So making it the most right possible is what would be the biggest number of differences. If we make it more restrictive, it'll be smaller. So we just want to count something that makes sense. Okay, so we're going to say 62, 99, and 100 wins. And we're going to actually say 2 of, so again, if you see a number, you should just assume at least. And I'm going to order these, actually. 62 loses. Okay, and I wrote does not win initially because we don't actually think of, when we buy a raffle ticket, we don't think about losing because you assume you're going to lose. Right? We buy it assuming we're going to lose, and you only think about it if you actually win. So that's why I wrote does not win. Okay, so now we need to solve this problem. Let's consider 2 cases. So case 1, 62 is a winner. Now I want you to figure out how to solve this problem if 62 is a winner, and then we'll check. Okay, how many people agreed with their neighbor on a solution? That's like 1/3 of you. How many people aren't done yet? How many people would like to tell me what's going on otherwise? So if you differed, I need to hear what people differed on. There was a lot of people over here that didn't raise their hand. You in the gray sweatshirt. Tell me what your solution is. You have no idea how to do this one. This is super easy. I've drawn the picture. I'm not trying to make fun, but this should not be hard. We've drawn the picture. There's one person wins, 62 wins. Out of these 3 people, we know 2 people lose, except we know that one already won, so the other 2 people have to lose. Right? And 62 we don't consider anymore. So if I know that 3 and 27 lose, and there were 99 people to start with, I have to take out how many? 2. So now there's 97 people to choose from. And how many am I going to choose? I'm going to choose 3. So you can redeem yourself. What do I do now? How do I write? Out of 97 people, choose 3. C 97-3. Okay. So from this group, how many did I choose? 1. Good. And then out of the remaining 97 that could possibly win, I chose 3 of them. And then what do? The last step. I order them, so I do P44. And then what do I add or just multiply these numbers or what? Multiply. Now we're done. Now if you want to be happy, like having some of the numbers add up to some total, you can do C11. And you can also do C20. So C11 is for this 62. So out of that 1 winner, I chose 1. Out of these 2 people, I'm choosing none of them. Now, the top numbers all add up to 100, and the bottom numbers all add up to 4. Yes? The question is, wouldn't there be an infinite number of ways to choose 0 from 2? By definition, it is given that there are 1 way to choose nothing out of something. So yes, there are an infinite number of ways. You could choose nothing out of that set wearing a red hat, dancing a jig. There are many, many ways, but we don't count them. Yes? I can't hear your question. Can you repeat it? No, we didn't assume that 62 won any particular place. So what we did first is we rounded up all the winners, and then we ordered them. So that's what this is. This is the ordering of the 4 winners. We're going to order all 4 of them. So once they're standing up here, then I decide which prize they get. So that's what the P44 is for. They go home. So the question is, what happens to the group of people that didn't win? So we didn't choose any of them, so they don't get ordered. But this is a fun question. You know, everybody here needs to know all the answers to all the questions that you all have. So I'm not trying to make fun of anybody, but this is not a super hard problem because we broke it down into one case where 62 wins. So you should know what happens to the rest of the people because we have enough specification here. Now, let's do case 2. 62 doesn't win. Now, why did I choose 62 as the one to pay attention to? Because 62 was the only one that was in both of those sets. So 62 was making it tricky for me to separate all the people into groups. So if I just get rid of him somehow, then it makes the problem easier. That's what you want to do, is figure out how to make the problem something you know how to solve that, and then go back and try to fix the problem to account for the things that you didn't account for when you solved it. So now we're going to do that. We're going to go back and say, okay, well, let's say the only other way is that 62 doesn't win. So therefore, what happens with this group? So the new problem is that one of 62, 99, and 100, well, not the 62, one of 99 and 100 wins, right? And what happens with this group? The 3, the 27, and the 62. So we can cross out the 62 and say one of these two loses. Right? Because we already know that 62 lost, so in order to get at least 2 out of the second group losing, I only have to have one more lose. And by the way, both of these mean at least. So now we're going to do this case. So we have our groups. We got 99 and 100. We have 3 and 27. And then we have the rest of the people. These are all of my groups, and they're totally disjoint, right? So now we're going to say how we're going to choose people out of each of these. So this is a really important thing. We have separated all of our people into categories. We've chosen 62 is going to lose, right? One of these will win, and one of these will lose. The problem is that these rest of the people don't stay the same when you do these other things, right? So out of this group, I'm going to choose how many? None. Out of this group, I'm going to choose how many? 1. Out of this group, I'm going to choose how many? 1 or 0. So I'm going to choose one winner or no winners out of that, right? Right, but as far as winners go, I might choose 2 losers, yes. Right, so what I can do is ignore this for right now, and I can break this into 2 categories. I can have, so we can do these 2. So after I do these 2, how many people are left? So that's 3 people there, okay? So I chose exactly one of them to be a winner, right? And one of them's a loser for sure. What am I going to do with the other one? Throw them back in the hat. So how many people are left? So we had 100. We subtract 62. We subtract another winner, right? And then so we have 98 left. So we have 100 people. We're subtracting these 2 people. And so now what we're going to do is we're going to say from the 98, we know that at least one of 3 and 27 lose, right? And 3 and 27 are not any of these people that we subtracted, so we know we're going to take at least one of these out. So there's 97 left of people that I might choose from to be winners, and out of those I'm going to choose how many winners? I'm going to choose 3 because I've only chosen 1 winner so far. So we can ignore this, but that's another way to do the problem. So let's try that after we do this. So we have C10 and C21, and then we order everybody, P44. So if the prizes were all the same, we just wouldn't do that last P44 step. So now let's do the problem if we did it that way and see how it comes out. Okay, in other words, we don't ignore this. So what we do is we say, okay, 62 loses, and then one of 99 and 100 wins. And we know that 3 loses, or 27 loses, or both lose. Right? That's our 3 situations for the losers, because we know at least one of them loses. So we have 62 loses, so he's out. So if we subtract that, we have 99 people. And if we subtract one of these winners, we get 98 people. And then we can have these three cases. So if we had 98 people and 3 loses, then now we actually have 97 people to choose from. The other thing we need here is that 27 wins, because then that's the only thing that makes this distinct. Right? So these 3 cases are actually, we have to have all 3. That if 3 loses, 27 has to be a winner in order for it to be separate from both losing. Right? Okay, so we had 98 people to start with. Then we know that 27 wins. So out of those 2, so before we did C21, out of these 2, 27 and 3, we're going to choose 1 winner. And then out of the remaining people, so it was 98 people were left before we got to that. And then we subtract 2, it's 96. How many people were we going to choose? 2. Case 2 is actually counted here already. So 27 loses, and 3 wins is actually already counted here. Why is it counted there? It's the same. I just chose from those 2, 3 or 27, exactly one of them winning. That's what C21 actually is counting. So now case 3, both of them lose. Then we do our C21 for 99 and 100, one of them winning. Then out of my 2, 3, and 27, 0 of them win. And out of the remaining 96 people, we choose 3 winners. And these are either or of these happen, so we add them. Now the inclusion-exclusion principle says that we also have to subtract the intersection, right? So if I add any 2 things, I need to think about whether there's anything overlapping in between those 2. But we specially made it so there's no overlap, so we don't have to subtract anything. Yes? Because we were specifying in the problem that at least 3 out of the set of 62, 3, and 27 have to win. At least 2 of them have to lose. So we already knew that 62 lost. So it was possible that 3 lost and 27 won, or 27 lost and 3 won, or both of them lost. So that's all the possibilities. So it could have been, if we didn't have that restriction, it could have been that 3 and 27 both could be winners, but not in this problem. Okay, so now after we choose the winners, again, we take all of this and we multiply by P44. So C21, C21, C96.2 plus C21, C20, C96.3 times P44 should be the same as the other one, and I'll leave that to you to check because we have some other problems to do. Questions on this one? That's right. So I'm sorry. Thank you for reminding me. We didn't actually finish the problem. We figured out 62 does not win, and we figured out 62 does win, and then we add those 2 things together to get our final answer. So thank you for reminding me. So this is just another way to figure out how many ways 62 can lose. So we need to add together case 1 of 62 winning, and that was C20, C11, C97.3 times P44. All that's times in between it. Case 2 was 62 loses. And that was C97.3 times C10 times C21 times P44. And so we need to add those because those are two separate cases and they don't happen at the same time. So we add them because it's an either or. So that's it. That's all we need to do. By the way, C20 is just 1, C11 is just 1, so that's going to be C97.3 P44 plus C97.3 C21, because that's just 1 P44. No, if you don't write the C11 or C20, I don't care. Yes. The question is, can we combine and simplify? Yes, you can. So if you come up with your answer in a different way, that's fine. So we will look for all the possible ways that your answer could be correct when you put it in. It will help us give you the most credit possible if you draw a picture and show us, how you did your choices. You know how I drew little circles with the people in it and said whether they were going to win or lose? That will help. And then you'll get the most possible credit for that. Now, if you just Zen get the answer in your head and you write it down, it's it's luck of the draw whether you write down the right numbers or not. Yeah, you can write in words what you're doing, yes. Versus drawing pictures, it doesn't matter which one. As long as we can tell what your reasoning is, then we will use that in figuring out if your answer is correct. Okay, let's try another kind of problem. Let's say we did a tree diagram yesterday, or the last time we were in class. And we talked about how you might need a tree diagram to talk about how many different kinds of ways you might play a playoff, where you have two teams playing each other. You're going to do best 3 out of 5 games. So just 2 teams, not a whole bunch of teams. So let's say we have 5 games, 2 teams playing, and of course there are 2 outcomes for game, win or lose. So Team A or Team B is a winner, and then the best 3 out of 5 is the wins. So the question is, how many different ways can the playoff occur? And this question is example number 22 on page 395 in your textbook, the 7th edition. There are lots of good examples. I highly recommend, again, that you work problems from your counting book, because the more you do, the better chance you're going to be able to recognize the problem when you see it on the exam. Okay. What we need to do here is we probably need to draw a tree diagram, because all the different paths through the playoff tree is going to tell us how many different ways the playoffs can be won. And the reason why we need to draw this tree is because after, let's say that Team A just won 3 games in a row. Do we play any more games? No. So we actually stop. So we don't actually fill out the whole tree. We actually stop whenever we figure out who the winner is. So that's why we can't just calculate it using some kind of formula. So let's say we have game 1 here. And we have 2 possibilities. A wins or B wins. And then this is going to be game 2. And then each time I'm going to put A on top and B on the bottom. So wherever I am, that level is how many games we've played so far. Okay, so where I am now is that I have AA there, I have AB there, and I'm just going to write AB there because we don't care about the order. And we've got BB there. So then at the next game, you have A and B as options. What we're doing is we're figuring out how many of each we have. So we have 3 A wins right there. This is going to be the end of the playoffs if that's the case. Then we get AAB. And I'm just going to have this convention of writing all my A's first. So in this case, by the way, what's going on in the middle here? That's the same thing. So we really could just say there's 2 of these. and we can just do an AB. So there's two ways to get AB where we were. And so then we can get AAB or ABB. And then here we get ABB and BBB. So BBB is also a finish, right? So we don't expand anymore after that. I'm circling the ones that don't get expanded. So now here, if we also go and combine like things, how many of those are there? How many AAB's ways have we got so far? We've got 3 because there were 2 here, because there were 2 at this joint, and then we added an A to it. So there are 3 different ones here. So there's 3 of those, and we can do an A and a B. And the same thing here, we actually have 3 of these too. So then we have AAAB, AABB, AABB, and ABBB. So circle the ones that are done. And how many ways were there? So each of these ones I've circled so far, there was just one way to get there. But there were how many to get here? There were 3 because I started with 3 here and then I added an A onto the end. So there were 3 ways to get there. Same thing here. There are 3 ways to get here. And then AABB, are we done? We're not done. So in this case, we're going to have to play the 5 games. So we have to do, both of these are the same, right? So now we'll do an A from here and a B from here. Now we had 3 coming here and we had 3 coming here. So how many are going into here? There's 6 different ways to get AABB. So now we have AAA, BB, or AA, BBB. So now each of these had 6 ways to get there because there were 6 ways to start and we just added a letter. So now we add up all the numbers that are at these nodes. So all the circled numbers are the ones we're going to add. Is there another way to do this? Yes. That's a possibility. So one possibility is to do half the chart, multiply by 2. That would definitely work, yes, because it's a kind of mirror image. I flip the A and B in the other half, yes. Solution down here. If I did a full tree, so if I played out, if I didn't stop playing and I played 5 games in every sequence, how many leaves would there be? There'd be 2 to the 5th leaves, right? So if there were a full tree, 2 raised to the 5th leaves. And that's what we're asking is how many leaves there are. So that's 32. So you could actually figure out what the full tree was and then subtract the subtrees that would have come out of these. So if I've already gone 3 levels in, I've got 2 levels left, right? And a full subtree with 2 levels has how many nodes in it? How many leaves in it? It has 4, right? So a 2-level binary tree has 2 to the 4th leaves. So I could subtract, well, I have to have a leaf for that, but some of those I'm going to take off. So I haven't worked out all of those, so instead of actually taking the time to do that, we end up taking off 12. There's another way to do it with that. But since I want to have a couple more problems to do, I'll work those. It's not a coincidence, by the way, that these are coefficients in Pascal's triangle. Okay, so the reason why we're moving on is because we have another problem. And if somebody wants me to finish the other reasoning for that, just post on Piazza and I'll answer it. Okay, here's another problem. There are n people at a party show that there are two people who know the same number of people at the party. What kind of problem is this? Pigeonhole principle. Excellent. So now we know that there's some ceiling of some number of pigeons, and it's equal to 2. Some number of pigeons have the same number of people. So now what are the pigeons? The people at the party, and how many are there? And then what are the holes? The number of people that you know. So the thing coming after the word same so the holes are the number of people you can know. So now we have to figure out what the number of people you can know is. What do we want this number to be in order for this to work? We want it to be no bigger than n minus 1. So we would like it to be n minus 1. So the thing you have to do in this problem is to figure out, is that number actually n minus 1? How many people can you know at a party? Everybody except yourself. So you can know n minus 1 people. But that's not, I don't know why. Let's count yourself. Okay, so you do know yourself. You can't say like, Tiffany Barnes, I don't know that person. That's not allowed. Okay? So knowing someone is going to be reflexive. Okay, so actually the number of people you can know and we assume you know yourself is I could know one person all the way up to n people. Now, if you can't know yourself, by the way, it is the same. It's just that it's 0 up to n minus 1. And those are actually still the same number of people that you can know, which is n holes. Right? Yes. No. We know ourselves. So the maximum you can know is all the people at the party, including yourself. So both of these is n holes. And that's a problem because we need it to be n minus 1 because otherwise it's not going to work. The Pigeonhole principle has to have the top number bigger than the bottom number for it to round up. So this is a situation where we have to break it down into cases. And the case I'm going to consider is, let's say you have some party crashers. What are party crashers? Have you ever crashed a party? Okay, well let's do the no party crasher since no one here crashes any parties. I don't believe you guys. Like, you live in dorms at least once in your life and you're passing something and there's some food and there's people. Nobody knows everybody there anyway. Okay. Fine, none of you ever crashes parties. Okay, so if there's no party crashers, how many people can you know? If there's someone who is a party crasher, how many people do they know at the party? They don't know anybody but themselves, right? So that means that if we're using this case where you know yourself, okay, we're not using this case, then you cannot know one person at the party if you are not a party crasher. You have to know at least 2, right? Yourself and one other person. That's how we're going to define party crashers. You don't know anybody at the party if you're a party crasher. We're not going to be picky about invitations. We're just going to define a crasher as someone who, it's not a wedding, right? Weddings are expensive. Just any party. where there's like pizza. It's cheap. It doesn't matter how many people are there. So, yes, we're going to assume that party crasher means just you don't know anybody there. You know, like wedding crashers? Like those guys, they just go to weddings, and they don't know anybody there at all. They go there to pick up girls. That's the premise of the movie. The movies. Okay, so there's no party crashers. So the number of people you can know is what? What are the numbers? It's possibly 2 up to n, right? Those are the possible numbers of people that you can know. Because you can't know 1 because party crashers only know 1 person. And we said there aren't any party crashers, so there's n minus 1 possible numbers of people you can know. And so, yay, our pigeonhole principle is going to work because we have n minus 1 possible numbers of people you can know and n people at the party, so yay, we can round up to 2. What about if there are some party crashers? At least 1 party crasher. Now, does the host know that person? No. So there's a person at the party who doesn't know the party crasher. So actually, nobody knows the party crasher. So nobody can know everybody at the party. So that means that nobody can know n people. The most you can know is n minus 1. So you can know 1 person all the way up to n minus 1 people, but you can't know n. So again, we have a case where we have n minus 1 possible numbers of people you can know. So now we have this situation again, and we're happy because the problem is done. Okay, since we didn't have time to do a test review today, be sure to check on your Moodle. There is a recording with a Test 3 review. It's the same practice test. It's on iTunes University. And I wanted to show you one thing before you go.